yes, sorry again, it's no physics here, but
everything is physics.
Reality is information. So, so what I want to talk is actually starting from something, a very general structure called the lattice of information, and then see some properties of information theory on this lattice, and then extrapolate to leakage of programming language or deterministic systems. And so we start with this very general structure, lattice of information. We define it as it's basically the lattice of all partitions over a set, or equivalence relation. So you have a set of atoms, and then you take all equivalence relations over this set, which is the same as the set of all possible partitions. And this thing here is a complete lattice. So the complete lattice, the bottom element is the partition which has a single block where all elements are together. So that's the equivalence relation where everything is equated. And as top as the partition where a block is a singleton. So all atoms are blocks, and that's the identity, the components relation. And in the middle, so given any set of equivalence areas of partitions, can define the join by take all possible intersection block by block.
So your lattice are not the equivalence relations ordered by inclusion, but the quotients.
Sorry?
Your lattice consists of the quotients of this set. So not the equivalence relations of my you consider, but the quotients of the
class.
Yeah. No. Each element in this lattice is an equivalence relation.
But what you write there, what you seem to write there, are the quotients of the what you indicate there.
Sorry? This is the
partitions. Yeah.
But the partitions are the same as equivalence relation.
Yeah. Okay,
the partition is equivalence relation. Yeah. I mean, no?
Sure. But no, it's more about how you represent them. So you represent them as partitions.
In general,
you think about them as partitions.
Yeah, in general, yeah. That's it. And so the ordering is x something is below y if all blocks in x are refined by blocks in y. So basically, the relation is that if you have a partition where you can you split blocks here, then you get something bigger. And clearly, I mean, the one that you cannot refine anymore is the one that is the singleton, so that's the top. So this is...
sorry, which one is fine? The equivalent relation?
So if you have, for example, say this A, B, C, so you have, if this is X, so to refine that you could take this A, B, and C. So you split this block here into blocks.
That would be y.
This would be y. So this partition refines this.
Reverse inclusion of the set of pairs. Reverse inclusion of the set of pairs.
Yeah. So this is this is the object of interest. So I think also is well, these kind of things are everywhere. Imagine, the set of epistemic operators over a set that would be could be seen with this structure. And there is a notion of valuation on lattices from Birkhoff. Which is so it's a map from a lattice to real numbers, which is monotone and satisfies the inclusion-exclusion principle. So basically, you want to measure things, so you want to associate to an equivalence relation something that says its size, a number that says its size, and then you may want to say that the bigger the equivalence relation, the partition, so the more refined, the bigger it is, so the larger is its measure, and also that this measure is somehow additive, so you don't count things twice. So the inclusion-exclusion principle is that if you take the join of two elements in the lattice, so the measure of the join of two elements in the lattice is equal to the measure of the first element plus the measure of the second element minus the measure of their mid. Well, I mean, you can see this is related to counting two measures. Cardinality of set has this property. So if you take the cardinal of the union of two sets, you can take the sum of the two cardinals and then you take out the things that you counted twice, which is the intersection.
So the joiner was when you put two parts together.
So the join here, the join here you would take is the intersection blocks by blocks. So for example,
most common refinement.
Yes,
the intersection. It's the closure of the.
So typical. This is if you want to do So if you want to take the join of this, we take the intersection of all these blocks. So you take this, intersect this, so there you have A and then B, and then C. Indeed, yeah. So this is the top element, so the soup of this. The meat is a bit more involved. So the meat is you have to take basically is the union, but then you take the transitive closure of the things. That,
do you get the sort of higher order inclusion exclusion from that without any assumptions on the matter? So you take it on three things.
Well, here there is no some. I mean, for example, the relative information is not distributed.
I know, so I'm just saying, but there are these higher order inclusion exclusion things, like if you take a joint of three things.
Oh, right.
Things.
Yeah.
So can you, without assumptions, can you derive all of those?
I don't think so. I would think so. Now, the first connection here with information theory actually comes from this formula, because there was a work from Raymond Young that showed that you could take information theory quantities as measures on kind of set-based random variables. So in particular, this inclusion-exclusion information theory correspond to this very basic equality, information theoretical equality. That, so if you can take the join of two random variables as the joint random variable, actually that's quite a precise correspondence. And so indeed, if you take the joint random variable xx to retrieve just the standard Shannon entropy. So take this, the joint random variable as the join, and then you take a measure of the intersection of the mid as the mutual information between x and y. Because intuitively, I mean, the intuition in information theory is that mutual information is a measure of the thing that x and y share. So indeed, you get the inclusion-exclusion principle. That is something that Young developed, and show that you can carry these things kind of formally to random variables. And this on information theory using Venn diagrams, for example. But this is not what we are talking here. In fact, because here x and y are not sets, are not random variables associated to sets, but random variables associated to partition, and this doesn't hold because this in the setting of partition, the measure of the mean is not the mutual information.
So the eta, function eta corresponds to lack of information. The function eta corresponds to the lack of information.
Why?
The analogy with the entropy represents lack of information.
Well, I mean, entropy represents a measure of information and uncertainty.
Yeah.
The negative measure.
Well, I mean, it's a negative measure of information, but I'm not going. Well, the thing now, the second step is actually that we can see this lattice of partition or equivalence relations as a lattice of random variables. Why? Because if we take the idea of a random variable, well, the feature of random variable as a map from events to a measurable space. Yeah. Now, from an information theoretical point of view of a random variable, this thing, it doesn't play any role. So if you take, for example, the random variable to throw a dice, and then you say 0 or 1 as value of the outcomes, from an information theoretical point of view, if you put to 0, 1 or 5 or 6, it doesn't change anything. The only thing that interests for that random variable information theoretically is that you have two outcomes with some probability, p and 1 minus p. So what you really are talking about, we are talking about the partition on your set of events that the outcome of a random variable generates. So you take your random variable, you take the outcomes, then you take the inverse image that gives you a partition on the set of possible events. And so you can see random variables as a partition, and so we can see this lattice of information. Once we have some probability on the atoms of the lattice, we can see this as a complete lattice of random variables.
Could you, are you talking about the support of the random
Yes,
variable?
yes.
So you're using the support to pass to this equivalence.
Yes, 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 yes. Because that's one of the things when people, for example, try to see the analogy between entropy and variance in probabilistic sense. Of course, there is an analogy because, well, it somehow measure sort of variance, but the things break down because variance relies on the outcome, whereas the information theoretical that function is only the support that matters. So now, if we see this lattice as a lattice of random variables, now we can go back to this notion of measure, of valuation, notion of Berkeley, and ask what kind of measure we can exist on this lattice. And here is what I need to talk about, which is Nakamura theorem. Which is, I think, not really known, and it says something quite deep about possible measures for this lattice. So the first thing is that let's start by considering a weakening of this exclusion principle. So we just consider this inequality, and we say that a map from a lattice to reals that is monotone and satisfies this inequality, so the measure of the join is less or equal the measure of the two sides minus the measure of their mean. We call this a joint semi-valuation. actually this is already in Birkhoff textbook. It's a classical notion for lattice. So now what, if you take the entropy map, so the entropy map is now if you take this as a lattice of random variables, then you can take the entropy of a random variable. So you get a map that takes element of the lattice of copartitions, and give you a real number. It's monotone, so it's that's simple things to check, that if a random variable is below another one by the refinement order, the entropy is also so ordered. But it doesn't satisfy the inclusion-exclusion principle, but it does satisfy this inequality. So that if you take the entropy of a joint random variable x and y, which is the vista per bound, then that is less or equal than the entropy of x plus the entropy of y minus the entropy of the mid of those.
Pasquale, but by entropy you just mean this eta, any eta?
No, that's Shannon entropy.
Ah, okay.
Sorry, yeah, that's Shannon entropy. So it's so you have so you take given a partition, so you take each block in the partition, and then take the probability of that block in the partition times log the partition on minus. So that's Shannon entropy, and that corresponds to the entropy of the random variable x.
What do you mean by probability of?
Well, here we are assuming that, so we have this lattice, and we have a probability distribution on the atoms. And then we take all possible partitions on the atoms. So each block, the partition of a block will be the sum of the probability of all atoms in that block.
So how do you get entropy from this eta?
This is just a general definition for you can put H instead of eta, so that formula there, and then you take the vista per bound of two partitions is a partition, and so you take that formula on the blocks of this partition here, and here, so you take the Shannon entropy again of this plus the Shannon entropy here, and
I suggest it might be very useful if you explicitly wrote how you get from a random variable. Even though you said it, it might be useful if you wrote it down how you get an equivalence relation from a random variable. Because there is a map there that you're kind of leaving implicit.
so from the equivalence
of the random variable, which is the thing you would have to do by.
So two atoms are related if and only if the random variable send them to the same outcome.
Atoms are equivalent if and only f of x is 0 and f of x prime is 0.
No, that's an outcome. That's an outcome. It's an outcome. Why?
Okay. F of x is equal to...
But it's a random variable.
Yes. So, I mean, if you have the outcome, giving outcome 5 in the total of dice, so you would have atoms...
There's many possible outcomes, right? You can't just say, it's not a function, it's a random variable.
Yeah, this is the fun, yeah.
Well, I'm taking the notion of a random variable as a function from an event space to a measurable space.
Yeah. A key that needs to be measured.
Yeah?
Well,
Maybe you should write some types down for
I think you should write some types down.
Well, I mean,
There's a map from the space of random variables to the lattice of partition, which is undoubtedly playing a role in this story.
so there is a definition of random variable as a map that associates outcomes to events. So you have you toss two dice, and you get an outcome. for example, having the result phi. You can get it in several things. All events that give you the result phi, all a pair of die throw that give you the result phi. Those are the outcome, particular outcome for that random variable. Yeah.
So f of x is a probability. F of x is a probability.
No, it's a real number.
It's a real number.
Yeah, f of x is the outcome. So having 2 die giving 5.
So if your big omega in your measurable thing for sigma algebra, you have a function to some set. You just want the inverse of this function to be measurable. That's it.
Yeah. And then, so the probability of this outcome is in fact the probability of the block that consists of all events that are mapped to that outcome, that give that the sum of all the...
So there's a little observation here that the entropy of the original random variable is the same as what you get by applying this. I mean, when you pass to the blocks, you're going to get the same number out, which is why it's okay to pass.
Yeah, yes, because these outcomes, they don't count any row. It's only the events that are mapped to an outcome, the probability of the events that are mapped to an outcome that play a role in the formula for a random variable. I mean, it's in general, yeah, you would write it's the probability of the random variable having a particular value x, so y, times log of p x equals y. So this would be the classical definition, but this is so. These are all elements. It's the sum of all events that have outcome y.
There's a little observation that that's factoring through this passage to the classes of information.
Yes.
Which is why you can ignore the outcome.
Yeah.
So the eters, they were actually we're not using the eters. It's just we've got the probability distribution on the events, and that gives us our h on the partition.
H is an example of an eta. It's not whether you're using the etas or not using the etas. H is an example of an eta.
I was assuming eta was somehow given and we were using it.
Eta is just the inclusion-exclusion principle for a map. And then, so this is a particular map. So this is, I'm now defining eta as entropy, is H. Yeah? But, point about entropy is that it doesn't satisfy this equality. It would satisfy if we were taking x and y as random variable over sets. But as there's random variable partitions, it's because the structure is different here for the meat. Then we don't have the entropy of the meat of x and y being equal to the mutual information between x and y. So we have this inequality. So so the Nakamura, so it starts by considering this inequality. So you take joint semi-evaluation, which are some maps that are monotone and satisfy only this equality, and the entropy is an example of such map. And he asks, his question is, if is it possible to define on such a lattice any other kind of joint semi-evaluation? And basically, the answer is no. So what he says is that, so you take consider a family Fn of functions for all possible natural numbers of continuous maps on probabilities. So Fn is a continuous map on probabilities P1 Pn. So such that have this property that if you take Fn of and probability P1 Pn, this is the same as Fn plus 1 of P1 Pn 0. So by adding a probability 0, it doesn't change the value of this family of functions. And also there are permutation invariants. So if you take P1 and Pn, then that is the same as the same value as the same function on any possible permutation of these probabilities. So we want f2 of 1/3, 2/3 should be the same as f2 of 2/3, 1/3. So the order of the arguments shouldn't affect the result, the order of the probabilities. Now, the thing is, if you have such a family, then you can build a map from this lattice of random variables to reals by doing this. You say that f of a partition x, so if you say that x has blocks x1, xn with probabilities, so here f of x is f of n of the probability x1, probability xn. Okay? So you can define, given a family of such maps, always a map that gives a real number for any partition, so for any random variable. And then now he's assuming two further things. He's assuming that, suppose now that this such f is also a joint sum evaluation, so it satisfies this inequality, so that if you take f of x sub y is less or equal to f of x plus f of y minus f of x plus y. And the second and last assumption he makes is that if you have x and y, which are as random variable independent, so are two independent random variables, then f of x sub y is f of x plus f of y. So that's, I mean, usually, if you have things that have nothing to do with each other, the measure of their them joining together should be the measure of the sum of their measures individually. And so his result is then such map f as then has this form, as the form minus c Shannon entropy. So you cannot define really a different joint sim evaluation. Now you could ask, but well, they could still be.
But in terms of partition, what does it mean that x and y are independent?
In terms of partition, no. You need a probability distribution and then see them as random variables. There is there is no coincidence. You really need probabilities there.
There's something that's been. Sorry.
How do you choose that when you define the capital X?
Oh, these are just the probability. So you have.
So those are given.
Yeah, you are assuming so that your set of atoms has a probability distribution that induces a probability on blocks for each partition. So you have, for each block in the partition, you have associated a probability, which is the sum of the probabilities of the atoms. And then, well, you have this family of functions that for each probability n, it gives you a value. And then, so you can define f of x in that way.
So he's talking about any joint semi-evaluation, but it has to behave in the right way on those, in the cases where the thing arises from probability distribution in this way. Is that the nature of his assumption?
Yes. So the probabilistically, well, it must be such that it's given by continuous functions that, well, it must be probabilistically based. So if you change the probabilities, it shouldn't, if you permute probabilities, it shouldn't change the value. If you permute the order of a block, the block's order in the partition shouldn't affect the value of the function. And then it should be additive, so when things x and y have nothing in common, then the measure of their distributive value should be the sum of their measures.
There's something that's been bothering me all along about the joins. So if x and y are random variables, then you get the partitions from them. And you know what it means to take a join of two partitions, what it means. But in going from the random variable to the partitions, we've lost the information about what the real values were. So is it obvious that when you know how to join or meet partitions, you know how to join or meet random variables, or does it somehow not? Well, or maybe if that's not true, does it not matter?
The joint random variable is well, is the intersection of blocks. Is the event.
Yeah, but that's what I'm saying. Just knowing the block doesn't tell you what the
we
random
don't care
variable
about
is.
the values.
You don't care, that's the thing.
Right. So
It's all about the way in the first place to get into these blocks.
Yeah.
so what?
It's just labels.
And that, I mean, it's in general, yeah, the correlation between two random variables has nothing to do with their values.
Okay. So Samson said we're just using.
It's the same as
The real values
joint
as
operator
labels.
when you go to the projective spectrum and forget
Yeah,
about the values.
yeah. So you're using the eigenvalues as labels
You
of the
throw them away.
eigenspaces.
Yeah, just identifiers to distinguish.
Oh.
So now, so this is Nakamura theorem. Now there is a simple addenda to this, is that, well, so now we know that all joint semi-evaluations must have this form, must be up to a constant the entropy partition. But, so in particular, if there were to be a evaluation, so if there were to be a map that were to satisfy the equality, well, it would be in particular the joint semi-evaluation, so by this theorem we still should have this property. But in fact, it's very easy to show that that cannot be the case, because the entropy, well, you can find a counterexample to the equality for the entropy. So basically, the conclusion is that entropy is, well, the best measure that you can build, best in the sense of satisfying these kind of properties that are classical in lab.
Only measure you can do that. Not the best, it's the only one.
Well, that satisfy these properties. Yeah. But, so,
There have been other entropies proposed.
sorry?
There have been other entropies proposed. I mean,
Yeah, but none of those will satisfy.
Some will typically fail.
I'll show you in a second.
What's the name again of that guy? Because I can't read it.
Nakamura. So this, maybe I'm wrong, but when we found this article by chance, this is the paper from the 60s with 0 citations. So nobody ever cited this paper, and but I think it's quite a deep result.
And you've increased the number of citations.
Yes, actually, yeah, I think now it's mainly all our paper that cite Nakamura.
We'll send you a postcard for Christmas. Still alive. Yeah.
Well, I mean, it's a different result because it's something, it's very general, so it's just any lattice where you have probabilities, and the only thing that you can do is this way of measuring stuff. Now, the other thing...
So, so you take any set, you take any probability measure on it, you build this lattice, and then the entropy, the only one would satisfy the equation at the bottom. The only one.
Yeah.
Not up to blah.
Up to a scale of multiple.
Up to scale of multiple blah.
So, now another thing that is not, I think, maybe well known, that is a Shannon note. So there is a Shannon note by Shannon, is in his collected works, and it's called, I think, a lattice theory of information. And I think it's very interesting, very related to this. So his point is that in his main work, Theory of Communication, Mathematical Theory of Communication, well, the title is a Mathematical Theory of Communication. It's not a Mathematical Theory of Information. And then he argues that what information theory does, entropies, is really to measure information, but is far from giving a characterization of that. So as an example, take, so I don't know, costing a coin. So you can have a head or tail, and then you can take a presidential election between two candidates. Yeah. So here you have two kind of processes, two random variables that have two possible outcomes. They could have a very similar measure, around 1/2. So the entropy would be around 1, would be a very high entropy. But they are, well, completely unrelated. If you know who won a particular election, you are none the wiser about what your next coin value will be, and vice versa. So he asked himself, what is a characterization of information, not just a measure of it. And says, well, one thing that we could say is to take sort of a family of stochastic processes and then consider the things that came out by reversible transformations. So if you have some text X that is written in Morse, say, and then you have the same text that is written in English, then knowing this, it tells you everything about his translation in Morse, and vice versa, knowing the Morse code will give you all the information just to know it in English. So what happened here, if we put some formalism, is that what we are talking about is the conditional entropy, so it's the uncertainty about something given something else. So here, the uncertainty about the text translated in Morse code, given its source being in English, is 0. And vice versa, so if the English given X Morse is equal to 0. So the fact that the conditional entropy are 0 in both directions is what Shannon suggests as a characterization of information. So he says, in this lattice of processes or random variables, we're going to define a map D, between X and Y, as a conditional entropy on X given Y plus the conditional entropy on Y given X. And this map, it turns out to be a pseudometric, so clearly symmetric, and is under inequality. It doesn't satisfy that if two things have a distance 0 are equal, but if they are the same, they have distance 0. So it's a pseudometric, and these points that have distance 0 as what is suggested as the information item. So now, well, we can play with this thing, and we can say that we can define the following order. We can say that X is less than Y, if and only if Y provides all information about X. So if we know Y, there is no uncertainty about X. And then, well, it's clear that d of x, y is equal to 0, if and only if X is less than Y on this sense, and Y is less or equal to X in this other sense. So if they are both one below the other according to this order, then they are the same information item according to Shannon entropy.
Is the h of x given y, is that a quasi-pseudometric?
Sorry?
Yeah.
This is a pseudometric.
It has the triangle in
Yeah,
the policy.
yeah.
No, the h.
No,
Is it, yes, and I think Samson's are.
yeah, I think, yeah.
No. Well,
I mean, in other words, the pseudometric factors are a non-symmetric thing.
Yeah.
which is just the one term.
Yeah, yeah.
Are you certain about that? Because I think you need the symmetrized version to get triangle.
Oh, really?
I think so.
What
certain.
made me wonder was the plus in the middle. If it came from a max, you'd kind of believe it. And I'm wondering if the plus...
Not sure.
Not sure, okay.
Sorry, yeah. Well, why why I'm interested in this order coming out from Warsaw definition is because, in fact, we retrieve the order we start from on lattices, on partitions. So if we take now x less than y according to this definition all over possible probability distribution, so for all possible distribution mu, x is below y, for all possible distribution mu, the conditional entropy of x given y is 0. Then if we take this definition, then x and y
Sorry,
are...
the x and y are random variables.
Sorry?
The x and y are random variables, each with their own...
Well, we take their support.
Yes.
And now we are going to change, we're going to consider all possible probability distributions on this support. For each one of these choice, we get, well, slightly different random variables for which we going to measure the conditional
So
entropy.
if I give you a mu, how do you recover the random? That's just so there's a common distribution that applies to both of them.
Yes.
Yeah, I mean, sometimes you think of random variables.
On the atoms, yeah, the distribution, yeah, yes. So, so this is the first thing that we're going to link, so that we can recover so this refinement order in terms of Shannon order. So in particular, the things that are ordered to the refinement correspond to Shannon that are equivalent for the refining order as what correspond to Shannon intuition of being the same information. But now, so the other thing is that also we can do the similar experiment with entropy. So, and then we get the following result is that again the refinement order x is below y if and only if for all possible distribution the entropy of x is always below the entropy of y, no matter which distribution we take on the atom. So again, the refinement order is characterized simply by their entropy. Well, one side is clear because the joint sum evaluation is monotone, so this side is given by the fact that we know that the entropy is a joint sum evaluation. Is the other direction that now, so we can do some other stuff. So now we can take other notions instead of say information theory, take probabilities.
Pasquale, how much time do you need more? You're 11:05 now.
Well, then I just write stuff because here. Well, but basically, so now we can ask the.
Prakash, I've been videoing for 43 minutes. That's helpful.
43? Really?
Yeah, we started
Must have
quarter
started a
past.
little bit
You
late.
started so late? Okay. Well,
So anyhow, you can define now on this partition, so on these random variables, notion of likelihood of guessing one atom or one value in n tries. So if you have a set, you say that guessing a value in n tries given a particular distribution, you take the sum, you assume that probabilities are ordered, so x e is greater or equal to x e plus 1, and then so you take all the sum of an element with the largest probability, and that gives you basically the probability of guessing one particular value in n items. And then you can so bring this over a partition just by taking this definition block by block. So this is related to kind of to Minent, we will see later. But what happened is again that if you take now this definition of lattice of information, you have that to be ordered by the refinement order, it means that is the same as for all tries and for all distribution, G and mu of x is less or equal to G and mu of y. So that is always more difficult to guess things in y than in guess, no matter what distribution you take, no matter the number of tries. And the other thing also you can do, so people express so probability of guessing things, also the average number of attempts that you need to guess something. And there, so you given a set, you can take the number of guessing for x as the sum I greater or equal to 1 of p xi. So again, we assume that things are ordered decreasingly. And again, so here again, it's counting the average number of attempt you need to guess some particular value. We can again export this definition to partitions taking this definition set block by block. And again we have the same thing, is that the refinement order, well, here clearly cannot be in the same order than before, because clearly if something is easier to be guessed, so if there is less uncertainty, it will take less try. So actually in this case is, if I believe, for all possible distribution, it will always take more attempt to guess x than y. So x provide less information, y provide more information because it's higher in the refinement order. So it will take less time to guess y because there is more information than x. So so this kind of is the picture for what to give for the lattice of information, so that we have all these equivalences between, so it's refinement order, Shannon entropy, Shannon ordering coming from this distance, probability of guessing the secret in n tries, and number of tries needed to guess the secret. Now the other, so now I wanted to connect this with the semantics of this leakage of progress, but I don't think I have time.
No, you have apparently more time than I thought, so you're sure about
48 minutes now.
10 minutes.
10 minutes more.
Well,
He's not
for
sure.
the
How many?
you want one, yeah. And in fact, it's also the case that this equivalence holds for just n equal 1. So
10 minutes
So-
until it finishes 5 minutes left.
So what is different when we take, I was going to talk about the deterministic system. So the assumption made is that we want to consider leakage or quantitative analysis of systems where there is a functional relation between the secret and the observations. So given a particular secret, the observation that you can make is completely determined by that secret. So this is the setting. So in particular, if we take programs, the simpler setting that I concentrate is if you take a program, you take its rotational semantics, so that it gives you a map, say input-output, you take the output as observations, and then you take the inverse image of this map, that give you a particular partition in the setting I was talking before, a particular random variable that we can associate a problem. But you could take a different notion of observation. Some of the side channels you could take, for example, timing by having counters variables in the code that are observable and tell you the time that it takes to do some operations. But so what is the trick here about related to what I was talking before? Because there I've been concentrating on maps from this lattice of information to reals. Here, as Kostas was saying, the notion of leakage is not simply given by taking measures. If you remember what he was saying, it's about a difference between the initial uncertainty and the remaining uncertainty. So you have something that you know before running the program, then you see what happened once you run the program, and you measure the difference. And this difference is what the attacker capability has advanced. Yeah? And so this notion, they don't fit straight away in that setting. But in fact they do. So I can tell you, I can jump straight to the end. If I have time, then I go back. Is that, so if you have these deterministic systems where there is a functional relation between secret and observations, the following are true. Say that, so that a system is below the other in the refinement order, if and only if for all probability distribution, one is below the other in Shannon terms, if and only if for all n mu, so is always more likely to guess the secret in P than is more likely to guess the secret in P prime after any number of tries. If and only if the number of guessing needed to guess P prime is below the number of guessing needed to guess P. If and only if for distribution the mean entropy, so Smith entropy, that one that Kostas was talking of P is below Smith entropy P prime. And so again, if and only if the expected number of guesses to guess P. Now this is not what I was saying before. This is the other definition of guessability. So the number of guessing that are needed by defined in terms of the difference, so in terms of the remaining number of guesses. You have at the beginning you needed a certain number of guesses. After you advance your knowledge, so you may need more. So that's the difference. And and all this. So all these notions in these settings where you have a functional dependency, functional relation between the secret and the observation holds. So it doesn't matter really if you like Shannon entropy, you like Renyi entropy, you like the number of guesses you need. In this context, when you are concerned about relating to programs in terms of their leakage, they all come out to be the same. And I think I'm more time, no?
5 minutes more.
I got my 5 minutes more. Okay, so then.
Did you want me to say no? You have no more time.
I got 20 more slides.
Maybe you can take questions because Katisha is burning to ask you questions. Okay.
Well, what I wanted to show is that not just this equivalence, how all these things, all these approaches, have the same narrative. Now I'm going to talk about the numbers that they give. Here, the relation doesn't tell you what this number is, it just tells you that this number will be less than the other number. But now I'm going to try to argue that actually they make sense in terms of the numbers they give. So here is an example from Yatsuoka Terauki of two small programs that you have. First is a password check. If the secret is 1, then observe value 0, else observe value 1. And the second program is observe age, so you leak everything. So here we have a little leakage, here we have you leak everything. We say that age is a 2-bit variable with a uniform distribution. So there are 4 possible values. And now, if we take all those definitions, we get all a bunch of different numbers, M1 and M2. So, if we take the entropy of the first is 0.112, the entropy of the second is like 4 bits, so it's 2 bits. If we take guessability, so the likelihood of guessing the secret, for the first is 0.5, second is 1. If I take the expected number of guessing is 1.75, here is 1. If you take mean entropy, so this is Smith's definition, you get for the first 1, for the second 2. And if you take the number of guessing in terms of the difference, you get 0.75 and 1.5. So now I'm going to explain what these numbers means. So let's start. The second is easier. So the second, we started. This program leaks everything. The observer knows the secret. The secret was 2 bits, so he knows 2 bits. So as everything is leaked, we are sure about what the secret is. So the probability of guessing the secret is 1. And also, the number of tries to guess the secret is 1. We just know, so we just say it's that. Now, at the beginning, it was a 2-bit variable for possible value, 1/4 probability each. We had an initial uncertainty of 0.5. The initial chance of guessing it was 1/4. Now is 2, and that is a 4-fold increase. So what we have is that 2 to the mean entropy of M2 is equal, so 2 squared is equal to 4. So this is the exponent that tells us the increase in our chances of succeeding from the initial chances to after running the program. And the average number of guessing, which were at the beginning were not 2.5, so we had 4 values equally likely. We needed on average 2.5 number of guesses. Now have been reduced by 1.5, which is this quantity, to ng1 to 1. So we have 2.5, we have reduced our number of guesses needed, and now we have 2.5 minus 1.5 is 1. Similarly for the first, so our uncertainty, so for the first, well, we can start from G0.5. So our chances of guessing the secret is 0.5, because we have here we guess surely in this case, and here we have chances that once we wait we get 0.5. So the chances of guessing have doubled at the beginning. So we had 0.25, so now we have 0.5, and so that is why M1 is 2 to the 1, so I've doubled, so the factor is a 2-fold increase. The average number of questions that was initially 2.5 has been reduced by 0.75, so that now it will take on average 1.75 guessing to guess the secret. And the initial uncertainty has been reduced by 0.811. So you can put basically these notions kind of in a big soup and make them a consistent narrative about the values that you get. And this is related to, well, the property that can be expressed formally, but I don't have time, so that's okay.
Right? Any questions? Costa?
So you have here, so this is just saying that all these uncertainty measures actually so impose the same ordering of programs, right? So can you identify what is the common properties, or the property that is sufficient for that, or maybe also necessary and is shared between all those? And what is the reason why all those?
Well, it's because it's essential that you're going to take into account all possible distributions. Is that really, if you can, well, you can basically play with distribution to concentrate weights on points that may be able to distinguish them. But if they are in the refinement order, there is only one way you can distinguish them. That's the.
Okay, so maybe you can formulate this as a, a concrete property, and then show that this property alone is enough to do that.
Am I right guessing that the refinement on program coincides with the refinement on program series functions?
Indeed, yes, yes,
so
yes.
It's exactly there.
Yes, yes.
So these equivalences are under the assumption that knowing the secret completely determines
Your observation.
A secret cannot give rise to different observations.
right, so presumably these things will differ under a weaker assumption.
Yes.
Yeah.
So
Yes, yes.
So is there any, I mean, do they appear in different strengths then? Under a general assumption, some notion find the others, or are there just not very clear relationships between them? Are they comparable?
The same. I wouldn't know.
So in fact, this is very related to group anonymity. That what you're told is that the group anonymity is when this idea that you can make a person anonymous is completely indistinguishable from other people. So to make the same a certain group of people generates certain observable, then as large, the larger this class, this group of people is, the more anonymous it is.
Yeah, yeah, yeah. So, yeah.
So this is very nice. Yeah, there's all these papers about group anonymity, but there is no, the foundations of ad hoc practice of this group to write a very nice and elegant framework.
Yes, indeed. Okay, let's thank Pasquale again. Okay, Bob, we give you a special question.
No, it's more a historical question. I'm kind of surprised that this Nakamura theorem, it's not a theoretic characterization of processional entropy, right?
Yeah.
That's exactly what it is, and it's from the 60s. And say it hasn't been picked up by anybody.
Yeah. It's well, it was picked by a student of mine, and then he said, because we were interested in this lattice, and then I told him, I mean, this result is on page 20, and it took me 2 weeks to get it there, and to understand the context. But I think it's a very deep result.
It's a beautiful result. It's not purely order theoretic. There's this relation. It seems to be a
the random. You don't really care about the values of the random value.
No, that's not the issue. The issue is the nevertheless these assumptions, right? Things you've actually got written down.
This.
Yes.
Yeah, but I mean, I think these are really fundamental.
I'm not disagreeing with them. I'm just saying
They're not order
theoretic.
theoretic.
They're not, indeed, yeah.
So there's some permutation and variance, I think, is a key part of any of these proofs.
Yeah, indeed, yeah.
Symmetry.
Yes.
Yeah.
So there's a derivation of Shannon entropy, also ED characterization from 4 axioms, right? They actually resemble.
They resemble,
these.
yeah.
So one
In-
of them is
In fact,
One of them is exactly this.
yeah.
in fact,
2 of them are exactly this.
in fact, that's the. In fact, but somehow, I think this is a even deeper characterization of.
I agree.
Yeah.
Agreed. Any more questions, Paul?
No.
Marnoush? Have your hand up? Okay, thank you. 3 times. Only Pasquale gets thanked 3 times.